I'm going to talk about IEC 61850. I think there are a number of places where this protocol is being used, and it's actually becoming much more popular than currently being used. There are many areas that are trying to use this protocol. So I thought I'll give you a brief introduction to this standard, IEC 61850 standard. It's over 1,000 pages, and I'm going to try to condense this in 1 hour. Okay, so let's see how it goes. And I want every single one of you to ask me a question. Okay, I'm serious about that. I just don't want to lecture. I want interaction. Okay, because lecturing I could have done sitting in Canada. There was no point for me to come all the way here. Okay, so we want to have interaction. So when I say everyone should ask a question, I am very serious about that. Okay, so let's start. And before I do, how many of you are familiar with computer networking? Few of you, computer networking, right? How many of you are familiar with this particular standard? Few of you are familiar with this particular, so maybe you can contribute to the discussion, okay, based on your experiences. Okay, so I will try to cover both, and very briefly, and then we will talk about important aspects of IEC 61850, which are important from cybersecurity point of view. I will not be able to cover everything about this standard, as I said, but aspects that are important from cybersecurity, because later on, I'm going to talk about a standard that secures this standard. Okay, this standard by itself is not secure. It's being used by utility, but it's not a secure standard. But before we do that, I want to talk about public key infrastructure. How many of you have heard that? Public key infrastructure, one person? Okay, so we are going to spend at least an hour on that with examples and so on. Okay, so let's make these sessions interesting, not boring. Okay, we want to make these very interesting, because the idea is to learn, and I want to learn from you also. Okay, so this is what I will do in this session. I'll give you some networking basics, those who have no idea about computer networking. Okay, because this standard is very much about networking. Okay, and then we will talk about very briefly what are the existing standards that are being used and what are their limitations. Then we will talk about IEC 61850 standard, only the aspects that are important to cybersecurity, data transfer, various modes of data transfer, and we will summarize, and then every one of you will ask me a question. Okay. So this one I don't need to do too much, why we are doing this, what is happening in the power sector, and so on, right? Things have changed, and and this standard was in the making for 10 to 15 years. It took 10 to 15 years. Actually, even before it started, discussions start happening in IEEE Power System Relaying Committee. Okay, so we would meet. So Relaying Committee met Monday, Tuesday, Wednesday. Thursday afternoon, this group met. And IEC 61850 was born after that group. Okay, so I was part of some discussions initially in that group. Okay, so communication, as Professor Walda mentioned, it really plays a very important role, and it's become central. So whenever there is communication, there is going to be a cybersecurity aspect. There is a danger, right? So we collect the information, we exchange the information, we are going to process the information. All this digital thing, it's good, but at the same time, it has really created a huge problem. And from the cybersecurity point of view. Okay, and this is an area that's going to gain more and more traction because a lot of problems have happened in the last 10 years or so. We have 70% increase in cybersecurity incidents. And unfortunate thing is that many companies do not admit it. They are trying to hide that and problem because it's a public perception because they are not doing their job and so on, right? So so it may be even a bigger problem than what we see. And a lot of the commercial companies, it's mainly ransomware. They want money basically, right? So these are, I don't say small criminals, they are smart criminals. Okay, so they basically intend, and and power system is no different from that. It's they are very much vulnerable to that. The only saving grace is that in the power system, the number of points where a cyber attacker can get are limited. Okay, and we will talk about that later on. Okay, it's not, the surface is not very big. Okay, so again, when this standard was started, there were certain aspirations. One was obviously interoperability, that various devices can talk to each other from various places and so on. And the other one was obviously to reduce the cost. Okay, so hard wiring, a lot of copper can be saved with this one. And the third aspect was really to make things efficient and much more economical, and provide additional functionality as well in the process. Okay, so let's talk about the communication. So 2 minutes, maybe 3, to explain to you computer networking, and you tell me how I did after that. Okay, so basic components of communication. Application which requires communication, that's the first component. The rules for communicating, okay, which is no. And they are at a audible distance. That means, transmission can happen. Okay, so those are the requirements. So this is Smith's brain. Okay, ears, mouth, and the brain. Okay, so in that brain, there is one part about knowledge of science. Okay, there is another part, knowledge of English, because remember, they have to understand the language, right? And then there is third part, which has information about Julie. want to communicate with Julie, right? You have to have information about the other. In our case, it will be device, right? And then they have to be able to control their mouth and ear, because if they want to discuss and both of them speaking at the same time, nobody will hear. So same thing will happen in computer networking, right? So, and then you need a way to convert the information sound waves, back, right? So this is the Smith's plane. Same thing with the Julie. They have to have the same situation. Now they want to communicate. What will happen? They want to talk science. You think they can do that at this level? They can't until now, unless in the future, something happens that without talking and all that, we can just, communicate science. So this is one layer, right? You need that layer, but they can't directly communicate. This is the second layer, which is the English language layer. Still, they can't communicate directly, right? Until somebody speaks and somebody hears, right? You can't do that. And then they need to know information about each other, because we have accent, sometimes, we say words differently and so on. So they need to know. So devices, in a way, need to have information about each other, right? And then we have ear mouth control, right? They have to have that so that, they don't talk at the same time. And then sound wave conversion, so that they can hear and convert that, okay? So each part cannot communicate directly, right? So what has to happen is everything, let's say Julie talks. Smith is going to, interpret that. First listen, control the ear, have information about Julie, understand English language, and then and only then understand the science part. So everything Julie is saying has to go through all these layers. There is no direct connection. Same thing for the Smith. Okay, so these are the layers. Exactly same way our computer networking has layers. Okay, and the purpose of those layers is what I described earlier. Okay, reliability, loss of data, and so on, right? So, so this is, well, obviously physical medium. Here it's, the air, right? They have to talk. So, and these are the protocol, obviously understanding the information also, the way it will be presented, right? So same way we have computer networking, and this OSI reference model is the one that we use, okay? And modules are arranged in a vertical stack, just like, I showed you with that example, right? So application layer cannot talk to application layer of the other device until unless you go through all these layers, okay? So we start with the physical layer, okay, which is obvious, right? You convert your information into bits, zeros and ones, and then transmit over this physical layer. Could be a wire, could be fiber optics, could be anything like that, right? And then you have the data link layer, which is reliable transfer of information across the physical link, right? So every layer has a particular functionality, just like the Julie and Smith's brain, when they were talking. Every single layer has, we have a network layer, we have the data link layer, we have the transport layer, session layer, presentation, and application. Now, in order to communicate, sometimes you don't need all the 7 layers. In some cases, you can only work with few layers, and we will take examples, especially from IEC 61850, where we don't use all the layers in some cases. We use only, but obviously when you don't use all the layers, you will lose the functionality of these layers, right? For example, your internet uses only 5 layers, okay? So why do we care about this reference model, OSI reference model? And why are we even talking about when I was supposed to be talking about IEC 61850? Okay, so and you will understand when we talk about IEC 61850 and how it was built, you know, because there was a lot of discussion just on this part. Should we be using this 7-layer model? Okay. Now, the reason for this is because it was already standardized, right? Why do we want to reinvent the wheel? When we already have a standardized model that has been used for communication, computer networking for many, many years, why don't we use the same thing in power systems, right? So obviously it will reduce the complexity and also it's standardized. So manufacturers building the devices for power system can all use this, right? So, and it's modular engineering, you know, very simple. They are stacked on one on top of the other. It will standardize and ensures interoperability. Remember, one of the goal was to have interoperability. So we already have some interoperability in this. So why not use this? And it will accelerate the evolution, right? So we are able to do things very quickly because this already exists and obviously simplifies teaching and learning because people already are aware, they know about this. Okay, so this is your internet communication. It uses only 5 layers. Okay, physical layer, link layer, which is data transfer between neighboring elements. Okay, from one element to the other. Okay, then there is a network layer, okay, which is routing protocols. So it basically tells you over the network what is the best route available to transfer the data. And then transport layer, host to host data transfer. And we use protocols like TCP and UDP in that. And then obviously the application. Here it's HTTPS. In power systems, we will see what are the various applications that we use. So this is again, you know, you can use as many layers as you want. Then obviously you have to decide what functionality you want to build in. Okay, for example, in some cases we use only 2 layers, right? So depending on the application. Okay, so each layer has a specific function, just like, you know, science layer, English layer. Each layer has a set, and they provide their own services, which are only understood by the layer at the other end. Okay, so, you know, any other layer will not even understand that. So you have to go through each layer, right? So they carry the information from the layer below, right? So this is what happens, you know. You start with you know, layer 5, layer 3, layer 4, layer 2, and you build. You keep adding, and at the other end, you keep stripping the information till you require the. And obviously, this now creates a problem because all this requires processing. At every layer, you require processing. So it takes time. So your communication is going to take time. And that's a problem for power systems, especially where you want very faster response times. And we will see how this standard deals with that, right? So this is again more detail. I'm not going to go through every single one of these, and I think we are going to give them this copy of this. You will get a copy of this, right? So what is the application? It's the highest level, highest layer level in the, it deals with the application. Yeah. Not all 7 layers. Yeah. No, so when you are talking about that you don't need all layers, so obviously the standard that we are going to talk about, IEC 61, it is going to define which services need how many layers. And if all the devices are following that particular standard, then obviously they will all have the same number of layers. So communication is not a problem. Okay. So obviously, if they are not following the same standard, then they can't talk to each other. No. 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 They are tied to the standard, not a region or anything. Okay. So if you're talking about IEC 61850 standard, whatever is the standard saying, use 5 layers for this service or use 2 layers for this service. So every device, doesn't matter where it is in the whole world, they have to follow that. Not devices, different services. Yeah, different services that they provide. Yeah, so there you don't. So it's a service dependent. Okay, so obviously, if it is time critical, you can't go through all the layers. It takes a lot of time to process at each layer, right? But in some applications where they are not time critical, you can go through all the layers. So that means you get all the services provided by every layer. You have the reliability, you have loss of data, right? Which you can resend and so on, right? You have the routing information. So it really depends what service out of these you want to use. So yeah. Whether that particular attacker should also have the same type of so obviously, yeah, obviously this is the thing, disadvantage of standards is that everyone knows about it, including the attacker, right? So that's obviously they will follow whatever is there. Yeah, but there is another way to stop that, and we will talk about that later on. Yeah. Okay, so this is the application. I'm not going to spend a lot of time on this. Okay, this is the transport layer. It's basically a logical communication. Okay, in different company. So it's the sending side does some functions, the receiving side does some functions also, and it's basically providing reliable in-order delivery. And the most common protocol is TCP. So congestion control over the network, flow control over the network, and connection setup, so that they can talk to each other. So each layer provides different service, and this is the network layer. Okay, it basically determines the path, what is the best path to take within the network. Okay, and then moves the packets of information from, and then does the call setup, right? So each one of these have a specific function. And then we have the link layer, okay, which is between the nodes, between adjacent nodes. So it's basically one node and then the second node and so on, right? So that's what it is. And then obviously we have the, yeah, so no, no. So link layer is between node to node. Okay, let me just go back. So link layer is between node to node, right? From one node to adjacent node over a link, right? That we understand. Now let's talk about the to go back network layer, right? So main service is path determination. What path should it take? Because one node can be connected to multiple nodes. So which node it should go to now? You understand? Exactly. Yeah. And then there is physical layer, which is obvious, right? Zeros and ones are going on this. So now there are various protocols in substations. Okay, there are some proprietary protocols. Those are existing and still existing, and this is one of the problem in power system. It has been built over years, and we still have all these protocols and some of the new protocols and how to talk to each other, which is a big problem. And then there are open protocols, which are still used, Modbus, DNP3, and IEC 60. This is for the SCADA and so on, right? So those are some of the existing protocols. But the problem with protocols is they have their own data structures, right? And each protocol is ported different level of functionality. They can't provide all the functionality. Everyone have their own functionality, not easy to expand, and different standards are followed in Europe. So that's why IEC 61850 came, okay? So, and also the messages are not obvious. Data context is lost in the human machine interface. I'll show you what IEC 61850 is. This is just an example of a DNP3 message. You can't make head and tail of it, right? It's not obvious. It's not intuitive, right? Okay, so let's take a look. This is what the requirements. When interoperability, big thing, right? You want devices to talk to each other, so they follow same protocol. Pre-configuration, okay? So we used to say that you are an individual like everyone else. Okay, that's the key here. Yeah. So every device is an individual like everyone else. Okay, so you can be individual, but you are like everyone else. Okay, so that means you will follow IEC 61850, but you can have your own functionality. Every device can have their own function. And also long-term stability. This is very important for power systems, because people don't want to change things every 5-10 years. Power systems, they want to stay stable for a long, long time. So this is why the communication technology was not touched. So we ended up using the standard networking 7-layer model. Okay, so this is how it started. Okay, just a bit of a history. As I said, it even started before that. We were starting to have discussions before 1994, but 1994 through APRI and IEEE Power System Relaying Committee, we started what we call UCA, Utility Communication Architecture. It was not IEC 61850. Okay, and at the same time, IEC started their working group, TC57. They called it IEC 61850. So now two groups are working on same principle, right? We want to develop the same thing. So they said, rather than trying to do this, let's put this together. So between 1997 and 2003, a lot of aspects that were developed in the UCA were included in IEC 61850, except the goose. And we used to joke that European goose does not fly along with the North American goose. So, but eventually, obviously, the whole thing became one standard. Okay, this is a bit of a history. Okay, so there was a split. The focus was not on the communication part. The computer networking part stays 7-layer model. The focus was more on the standardization, was on the application side. Okay, so complete step split. So this is where all the standard work was done. Okay, application, switching devices, protection, control, so on, right? So this is what we have now. Okay, this is what it is. So these are the same that we talked about, and application, presentation, and session layers are combined into what we call MMS. Okay, I think it's called messaging manufacturing specification, and this actually came out of the auto industry. Auto industry had this system set up already, so then we decided why, again reinvent the wheel, use the same thing for them. And the focus was again on this, where we will talk about two things: data models and services. And we are going to focus on communication because cybersecurity aspect, communication is important, right? So we'll talk about that. So it's a standardized model for all applications, and we will see OSI 7, and there is a station bus and a process bus. Okay, the way it is set up, architecture, although architecture is very much flexible, but the way it is set up is there are station bus and a process bus. In the station bus, communication happens between ID and master station, and enter ID via goose. We will talk about that. Okay, and in the process bus also sampled values mainly, right? And the plant equipment. So this is what it looks like. So from the communication point of view, your substation will look like this. For example, you could have a process interface. These are your circuit breakers, current transformers, voltage transformers, any substation equipment where you will sample the data, okay? And those are through what we call merging units, okay? We will sample that data and put it on a process bus. And you can have multiple process buses. Again, architecture is very open. And also, you can even have copper wires in there because, older substations, everything isn't fiber or networked. You can have copper wires and go directly to your protection and control devices, which are then connected to the station bus. Okay, and then obviously you are connected to your substation computer and HMI and station gateway and go out of the substation. But you could have multiple architectures, multiple possibilities are there. So the current situation is many IEC 61850s have station bus. Very few have process bus. Okay, because process bus has some issues still. I think in the revisions of the standard that will happen, actually we have identified multiple issues and also given solutions at the same time in the process bus area. Okay, so this is the standard, and again I'm not going to, it's a 1000 page, over 1000 pages. I'm not going to go through all of it. Just want to give you an idea what is there in the standard. I will discuss two aspects only which are important from our point of view. First is just the system aspects, general requirements and so on, right? And then we have the configuration. So it has its own language, which is called Substation Configuration Language, SCL. Okay, so that's again a whole part where you can set up configure your whole substation, configure your IEDs through that language. Again, very intuitive language. Okay, and there are now software packages available that can be used to configure. Okay, and then there are abstract communication services. We will talk about those. What are those communication services that are available, right? And then data models. Everything is modeled so that it's standard, right? And this is mapping. Okay, we will talk about the sampled values. And then testing. Very little is done in testing. Actually, in the standard, it doesn't really, it's left up to the user to test. But those are the major parts in this standard. Okay. And again, I'm not going to go through each one of these, and you will get this. It's in there. I think in interest of time, I'm going to skip. These are basically details. And we will talk about the two parts, two aspects that I want to talk about. So part 4, part 5, 6, 7. So a little bit more detail in each part. But let's go on to these are the communication services I'm talking about. There are 3 types. You can have 3 types of communication within the substation with this standard. Okay. Client server communication, okay, which is slower. Let's say you want to transfer fault records from an ID to a substation computer. Okay. So it's connected to the substation station bus and so on. So it's not time critical, and also it's a lot of data. Your fault record is going to the station computer, right? So you will use all the services. So all the layers, networking layer you will be using, it will go through all the layers. Okay, because that's one type of service available. The other service is sampled values. Remember the process bus, the data is sampled. All the voltage currents are sampled, and sampled values are sent over the process bus, and any ID can access it, right? So obviously samples are happening every, let's say 1 millisecond, right? 1 by 1,000 seconds, right? For example, right? But it's nowadays it's even more. But they are coming regularly, right? So data is getting thrown on the process bus. So obviously, in order to transfer that, it's very time critical. So you can't use all the 7 layers, right? So what you have to do is you have to skip some layers. And so that's another type of service. And then there is a goose messages, which are generic object-oriented substation event. Any event in the substation, breaker opened, right? So that has to be communicated, right? Or you want ID want to open a breaker, that has to be communicated. So obviously there are time limits, right? You can't, if a fault is there, you can't go through all the 7 layers and spend a lot of time giving that message out. You need to give the message out right away. And actually standard puts the restrictions that if you're going to meet that standard, you must do that within, say, 4 milliseconds, right? So that's another type of communication that's available. Okay, we will discuss a little bit more about these. So goose messages, time critical, as I mentioned, trip, block, interlock, any time critical message, okay? And data transfer happens when the event happens, okay? Size of the data is very small. Obviously, you are just changing the status, right? And it does not use network, transport, or services of OSI, okay? It skips all those layers. It basically goes directly from the link layer, right? So, but that means you are not, it's not reliable. Okay, data can be lost, right? Whereas in the client server communication, you can, if the data is lost, you can repeat it, right? You can, go again. You can detect it and, repeat it. But here, there is no way of knowing that. So what do? They will do the multicasting. That means they will send the same goose message multiple times in the hope that at least one of those times it will get through. Okay, but there is no guarantee of that. And this is again a problem for utilities. Okay. Now there are ways people are trying to make sure that the goose messages get there, right? And then same thing for sampled values. We have current and voltage samples coming in, digital values, but this is a continuous stream. You can't even do multicasting here, right? Because one value is done, after some time, next set of values comes, okay? So this is a continuous time, and data size depends on the resolution. If it is 16-bit or 20-bit or whatever number of bits, okay? And it's not reliable data transfer, right? Because you can't go through all those layers, right? Just like the goose. And here you can't even do multicasting, right? So what you have to do is you have to deal with it in your algorithms, right? So, and then the third one we talked about is client server. Its data size is much larger, and you use the full services of the OSI model, right? So it's not time critical, right? So those are the three communication services that we use.
Client server, fault record, event record, that we are doing sample.
No, we don't send the fault records. Fault record is over, let's say, large size, and let's say you are doing voltage and current over 1 second, whereas sampled value is the current value now.
There we are getting the fault.
Yeah, in there, it's only, say, goose is only when an event happens.
Here
We are sending the whole record. Let's say fault happened, your ID recorded the data for 1 second, right? IDs can record the data, right? So fault happened, it's cleared, ID recorded the data, and now you want access to that data. So you will go to your ID and ask for the fault record. And there you use the client server communication. Yeah, because you don't, and there is no time issue, right? You can take as much time as you want. Whereas in sampled values, there is a time limit, right? Because the value is sampled, before the next one shows up, you want it transferred so that your relay can use it, right?
the sampling rate of the like particular network, or it will depend upon the like voltage like data. So you have the distribution system, and you have if the fault takes place, you doing the switching action. The percussion of the wrong switching action far more serious input. But if you take some small mistake, after effect will not be saved. So in that particular case, the sampling rate uniform for the standard, depending on the label, you will have the different sampling.
So it will depend on your device itself. So on your ID, for example, it will depend on that. Now, if you want to use data, at a different sampling rate, then obviously you have to convert that data to that sampling rate. Okay, otherwise, you will use the same. Time stamping will change. Yeah, but you have to then synchronize. So it depends what you want to do with that data, right? If you're using for protection, then obviously it's better to have the same uniform sampling rate, right? You will use that value under different merging units, right? So if it is not, then you have to compensate for that, right? In your calculation, you have to compensate.
So even if the protocol says that
Yeah, it is decided by basically your ID and the algorithm that you are going to use, right? Yeah. So the various ways you can access the data you can poll it. There is unbuffered reporting, there is buffered reporting, then logs can be done, and then peer-to-peer data value publishing. Two IDs can publish the data to each other, right? So there is a lot of flexibility even under those three services that I described. A lot of flexibility is there in terms of data transfer. So these are again different type of messages that are defined in the standard. Type 1 messages are fast messages, okay? For example, trip commands and few others, interlocking and so on. And the transmission time is 3 to 100 milliseconds. So for trip commands, it's 4 milliseconds, for example. Okay, all those messages are defined in the standard. And then there are medium speed messages, for example, RMS voltage. You want a RMS voltage at a particular point in the system. So those are medium speed, right? Type 2. And then there are type 3, which is the low speed. We talked about that, right? So 500 millisecond. And then type 4 is the raw data, sampled values, which is a continuous stream. So again, 3 to 10 millisecond, again, depending on the application. Okay, then file transfer is type 5. And then there is time synchronization data, because you want to synchronize all the devices. And usually that synchronization signal is over the network. And you can synchronize your internal clocks of devices. Okay, so that's another type of data that's there. But let's see how this data is represented in the entire system. Okay, so we have logical groupings. Okay, so obviously you have a physical device. Let's say it's your IED. Okay, which will have a network address, because remember, we are on a network now. Okay, it will have a network address, IP address will be there, and that's your physical device. Within the physical device, you can have a logical device. Okay, so this is not physical, it's a logical device. For example, ID1. Within the logical device, you can have logical nodes. Okay, those are again specific services for the power system. For example, this is measurements. Okay, this will provide the breaker control, right? And you can have multiple logical nodes. And how do you set this up? In the beginning, as I said, using the substation configuration language. You're going to set this all up using configuration substation language. Okay, each device, what it has. Okay, so there are actually 4 different type of files that are used for doing this. Okay, we are not going into details of that here, but you can set this up and specify the functionality of your physical device. Okay, and you can have multiple nodes. This is measurement, and all different nodes are defined in the standard. Okay, so these are again logical groupings. So those are different nodes we talked about, different logical groupings. So protection functions are P, and protection related functions are I for R, for example. And then there is switch gear, which is X, right? So those are all different groupings that are defined. And then there are 92 logical nodes, right? We talked about logical nodes. So for example, protection functions, there are 28 logical nodes within that. Okay, and for example, they are directional element, protection scheme, distance protection, and so on. And similarly for measurement, different levels, harmonics measurements, and so on. So almost everything has been defined that's possible. Okay, and similarly for the circuit breaker and the circuit switch, those are again different logical nodes. Okay, and then within each node, there are data classes. Okay, because node has to have some data, some information. For example, for measurements, there are 66 different data classes. You can have a AMP, angle between phase, voltage, and so on. So all this is defined there. Okay. So every single data point is defined, and you can have access to it, just by defining, going from the physical device to logical node to, to the data class, which is like a directory structure. It's just like a directory structure. So this is your logical node. Okay. This is your data. This is your data attribute. So you access basically just like a directory structure. So let's say physical device broken down into logical nodes. As I said, you can have multiple logical nodes. In a physical device, these are all different logical nodes. And within the logical node, you can have different data classes, right? So for example, take ID1, logical node XCBR, which is the breaker, and these are different data classes. Take a position of the breaker, whether it's open or close or bad state or whatever, right? So then all I need to do is to access that is say ID1 logical node position data class and what is the value, right? I need to just go there. It will return the value to me. Okay, right? So this is how all the data, possible data in a substation is defined. Okay, for example, I want to open or close operation, then that's what I will do. I will say XCBR position data control value, and I will say on or off. That's it. So if ID has a problem and wants to open or close a breaker, this is what it will do. Just send this command over the network. Right? So there it is. That's all it has to do. Right? So right? Opening the breaker and so on. So let's take, I don't know if we have time or we can come back because this will take, still we are not done yet. It will take a while for me to complete this. And maybe we could, we can start at 3. Yeah, we'll continue from here on, right? Yeah. But before we do, let's not forget what I said. So you already asked questions. You are off the hook. Yeah. Any questions so far? Yeah, please. Yeah.
You have defined some layer. All those layers are same for
Yeah, for networking, everything for networking, irrespective of the voltage level. Yeah, it's exactly same. As long as you are following this standard, that's the whole idea. And doesn't matter where it is, who manufactured that device, it will be the same. They can talk to each other. You can give these commands that I mentioned and get the information. Yeah, yeah. Okay, let's start. Which end? From which end we want to start? Any questions? Why? Sorry? Yeah, so in client server communication, you are basically, example is you are sending a fault record file. Let's say fault had happened, your ID recorded the data for, let's say 6 cycles, right? That's a huge amount of data, right? And then you transfer using client server. Whereas in sampled value, you are sampling a voltage Can I use this? So let's say this is your voltage, right? This is time, and this is the magnitude of the voltage, for example. And you are here in time, okay? So you will sample this value, convert it into digital number, put it on the network, okay? And then you advance in time, you are here now. You will sample this value, put on the network. It's one value at a time, but you want to do this as quickly as possible because this value is needed by the relay ID, which runs the algorithm by using this sample and maybe previous samples. Okay, so you can't afford to wait, right? You understand? Yeah. Yeah. Sorry? Yeah, routable goose. You are getting ahead of me now. We will talk about that. So routable goose obviously is using, but it uses UDP. It doesn't use TCP. It uses UDP. And UDP, it's better than regular goose, but still not, like client server communication. Okay. And obviously now you add time, right? You're going to add time because you are using UDP. Yeah. Yeah.
Hey, nowadays we can expect the cyber attack from any country, sitting anywhere in the
Yep.
you can attack anywhere.
Yeah.
So because here we are having the communication from source to destination in between two devices or two like so because like if we are having a national grid, we don't have any permission even for your neighboring country have any business at all unless until you have the international grid connection.
Yeah.
Then you will permit to if you are connected. But if you are not allowed, if you don't have any business with our grid, so how the person sitting in any other country will be like able to enter and get the access to our data, which is like the person is not permissible. He is not having.
Yeah, if they're not permissible, if you have put all the safeguards, then no. But the problem is all those safeguards are not there. That's the problem.
So like the person is just changing his color so that you will be not in a position to
Identify.
between whether it is a legal.
There are many ways, and that's what in the initial thing overview we was talking about. So it's if you have put all the safeguards, then it becomes very, very hard for anyone to intrude. But let me say this, there is nothing 100% secure. People will find ways. So what you want to do is make the things extremely difficult for intruders to come. Okay. So if you have put all the safeguards, it will become almost impossible for anybody to get in. Right?
Because the intruder is having the bad intent. He's not coming for welfare of man.
Yeah, obviously, yeah, they will.
He's intruding in your system.
Yeah, yeah.
It's like when you connect your electric vehicle for charging, and whatever is the charging backside connection, they are sending all data to the server. Servers are connected. Right? So you are giving data.
Like all this data is stored in terms of bits.
Yeah. Yeah.
So depending upon whether the particular data is MCD or LCD, according to the weightage will be more. Like if you are in the MCD, it is going to have some more value of, like, it will change the actual value by a large difference. But if you are having a LSP, like first, if you changing from 0 to 1 or 1 to 0, it is not.
Yeah, it depends what level of intrusion they have. So the impact will be that.
So according to the level of your digital data, binary data, then you go for the enhanced equal to your that particular. Because
So
going to have larger, it will suddenly change.
yeah, so
if you have the ID address and address, if you just change the MSP with one, it may have the different like instead of ID 1, it will consider the ID and
yeah, so level of intrusion will have different impact, obviously. But right now, there is no distinction between, level of security you provide for low-level data versus high-level data. Yeah, but right now, the problem is even bigger. We don't have security. Forget about, going one level down. We don't even have the basic things. So that's maybe in the future it will be, but right now it's a huge problem. Utilities I have seen, their ID passwords are 1, 2, 3, 4, 5. Yeah, they don't even change their passwords. Yeah, so yes, I know managing them, right? Exactly. Yeah. So this is why we are. Yeah. Yeah.
After 3 attempts, one is servicing can have.
Yeah. So managing is another aspect. Management of all that. We will talk about the public key infrastructure. Even managing the keys is a big task itself, right? So it's actually becoming a huge issue. And I don't think the companies, utilities, in our case, we are talking about the power system, are not there. Doesn't matter where they are in the world. They may be at different stages of providing cybersecurity, but there is nothing that they have achieved, right? The 100%. In my opinion, nobody has achieved that yet, right? So they may be at different levels, but there are ways to do it. You should start, and it's not one person who can do it. It has to be the culture of the entire organization. It's more a cultural issue too. For example, getting the USB from Somia and I put it in my computer. I don't know what he had on it,
yes.
right? Yeah.
Because if you are the static communication,
Yeah, and also the service providers. You have so many people coming into your utility from, your contractors and subcontractors and their contractors. So they're getting access at different levels. Actually, that's actually one of the incidents that happened because of a contractor. A big cyber incident happened, right? So there are examples like, so it's really, management is really a big part too of the whole thing. We can technically talk what we can do, but beyond that, it's culture and management. We will talk a little bit about that later on. Okay. Yeah. Yeah.
So nowadays, more IoT devices are integrating in our system.
IoT is another issue.
Yes,
Yeah.
so they are also using this IEC 61850 configuration, or if they are using, so which kind of configuration they are using? As you mentioned,
Yeah, they're not using this standard.
they are not using.
They're using different standards.
Okay.
They're using different standard, but their cybersecurity is another issue,
Yes.
right? With the IoT devices. Yeah. But some of their protocols um, are better actually in terms of cybersecurity. Okay, because what happened was, see, when this IEC 61850 was developed, there was really nobody talked about cybersecurity. You know, we are talking about 1994. It wasn't on anybody's mind. The whole concept was, let's make it interoperable. We want to do this, and nobody talked about cybersecurity. Later on, they said, oh, we should make it secure. And then the next standard comes, which we will talk about. How to make all this communication secure now. Okay, that's where this public key infrastructure comes. But before we talk about that, I want to give you some basic idea about public key infrastructure, because otherwise you won't understand what that standard is talking about.
Okay.
Yeah, IoT is another issue. I don't think we are discussing that here. That's the topic by itself, actually. Yeah, we co-founded a company some time back. Okay, there we are using IoT quite a bit. Okay, so are
Uh,
there any more questions?
so
Yeah,
EVs are also considered one of the IoT devices or not? Because in Bhalja's PPT, somewhere he mentioned like EVs are also treated as IoT.
the protocols are different too. Yeah.
They are following multiple protocols. Can sometimes demo so many
Yeah, that's another issue too. You know, yeah. So it's a very complex problem actually, not an easy problem. Are there any more questions? We are going to continue from here on.
Funny question from my side. How a power system engineer communicate with the technical to tell about the problem faced by the power system grid.
Oh,
What is the expected